module 2 category, because you are the new syllabus candidate. So your case, it will be module 2. So in module 2 second year, if you see, go and find the engineering dynamics portion, you will come across the detailed syllabus of it. Achha. First, before I go further, let me first present my screen. So you can see my screen, correct? Hello?
Yes, sir. Yes, sir. Visible, sir.
Visible. Okay, fine. Visible. Yes. Okay. So you know that the thing that I was talking about is the detailed syllabus. That syllabus you will get it from the JU website. That is number 1. Number 2 is regarding your book. Now this is the book that we will be going to follow. You see, this is the 7th edition book, easily available in the PDF copy in the website. So it is freely available, the 7th edition book. So this book we will be going to follow as our textbook in this class. Apart from that, you can consult other books also, but this is the main book that we will be going to follow for our day-to-day class proceedings. This is the 7th edition book. That is number 1. So this is about the book and about the syllabus that I have mentioned. So today we will go straight to the content of the class. So that's what I am going to take now. So with your permission, I will be going to now record the class from this point of time.
Okay.
Okay. Thank you. So there may be some spurious sound because my house is by the side of the road and hawkers always move by, dogs bark. So maybe some noise creeping recording. Anyway, so you see that this is actually our engineering dynamics. So let me open my board work for it. Oh, sorry. I'll open new one. Yes. So so this is the thing, as I was actually mentioning, that we will be going to study the engineering dynamics portion here, and the engineering dynamics here will be, basically we will be talking about, we see that the entire dynamics will be divided into two groups. The first one, we call it to be the kinematics. So we can write like that. So this is your total dynamics section, and this will be, this will be classified into the two categories. The first one we call it to be the kinematics. This we will say kinematics, and this is kinematics, and the second one we call it to be the kinetics. That is the first type of classification. In kinematics, basically you know that we discuss about the geometry of motion. So here we will basically talk about the geometry of motion. That means the effects of motion. Effects of motion. That means if motion is there, what will be its effect? So we can say this is the effects of motion. That is in our kinematics section, we will study this one. And in our kinetics section, basically we will discuss about the causes of motion. So that will be the case with our, with our kinetics portion. So this we will say that the causes of motion. So here we will discuss about the force, torque, etc., which will be required to sustain the motion. And in this case, we will talk about the geometry of motion. That is the first type of classification. Again, this, yeah, if you have any question, feel free to ask me at any point of time. Right. So, just let me join this one. Rishabh, okay. So, we see from here that this will be the kinematics and this will be the kinetics section, and again this entire kinematics and kinetics group, that means this dynamics group, will be classified into two ways. The first one will be termed as the particle dynamics. So that is the particle dynamics, means here it will be particle kinematics and particle kinetics, and then we will be having what is called as the rigid body dynamics. That is one type of classification. We are coming into detail of it. So that is one type of classification. In case of particle, essentially the body will be modeled by means of a geometric point or a particle. Correct. So if you have a system which is in motion, the system, say maybe it may be a car like this. Say suppose if you have a car moving on a flat road this way. So this is how your car is, suppose it is moving with certain velocity v. Now in order to analyze the motion of the car, if it is found that the physical dimensions of the cars are not important in studying its characteristics of motion, then we know that this can be entirely modeled as to be a mass particle here. So this is a particle. I'll show it like this. This is the particle or a geometric point, so to say, and all the masses of this system, you know, is being assumed to be focused onto this particular point. So if you see that the motion of the system is such that its physical dimensions are not important in studying the characteristics of motion, we can apply this particle concept. And majority of our problems, we can actually, you know, model it without committing much error, you know, that we can model it by means of a particle. So that is what is known as the particle approach. On the other hand, if in discussing the motion of the rigid body, in discussing the motion of a system, if the physical dimensions of the body, particularly the distribution of mass, right, that means how the masses of the body is distributed. For example, you may have a body like this, correct? So this body, you see, the mass distribution becomes important for the motion. How the mass is being distributed. Suppose if you say, let's take an example of a cone, say a cone like this, correct? So if I have a cone, you know, this way, and I just throw the cone with a certain velocity in air, then what you will see that this cone will oval, will execute various sorts of motion. And hello?
Translation plus rotation ki bolche na?
Yes. So actually, you know, it will be more important in case of the rotational motion. It will not be much important in case of translational motion. But in case of rotational motion, if you know that I want to study this system, then it may be that the physical dimensions of the body become important. Even in case of translational motion also, sometimes we see that the physical dimensions of the you know, the system become important. So it is not that only we require the physical dimensions or the distribution of mass in case of rotational motion, but also in case of translational motion we require the physical dimensions of the system in some definite applications. So in that case, in those cases, so to say, our assumption of particle right? That I can assume that our body is represented by means of a mass particle is not tenable. We cannot sustain this particular assumption. So under such conditions, we see we need to discuss about the rigid body dynamics. We say it is rigid body. It may be the deformable body also. You mean to say that in your strength of materials class, just the previous semester, where you have studied the strength of materials, in that section of our mechanics, or that branch of our mechanics, what we assume that the bodies are deformable. That means distance between any two particles, the distance between any two particles constituting the body, this distance is not going to be constant. Say in case of rigid body, this distance will be always invariant. That means it will not change. On the other hand, if it is a deformable body, of course the distance between these two particles, any two particles, that will change. In fact, if you take a third particle, then the angle between the two straight lines, they also get changed. So you see that comes under the case of dynamics of deformable bodies, which will be involved one. So right now we are not going in to study the dynamics of deformable bodies. It will be taught in somewhat higher section. So for us, therefore, that we may have this type of classification. In fact, I'll come to our syllabus content, that means which we will have to discuss in this class. So that is one type of classification. Now there is another sub-classification from here. That means this dynamics, it can be classified into three groups. The first one, we can say that your motion or dynamics is one dimensional. That is, just one dimension, right, is required to study the motion of this system. For example, if you consider this motion of this car, which is moving along a straight level road, right? So in this case, only one axis, right? One axis, maybe say in this direction, right, is required, is sufficient to discuss the motion. You understand what I am saying?
Yes, sir. So, yes, only the x-axis is required.
Exactly, but only one direction, or rather we say only one dimension is required for this study. So it is sometimes called one-dimensional motion, or it is called 1D motion. Then it can be the particle, it can be the rigid body also. So that is one type of classification that we get. Now in our second type, you see, we have what is termed as the two-dimensional motion. So you have two-dimensional motion. In case of this two-dimensional motion, it is obvious that only one direction is not sufficient. For example, let us consider that you have a small ball, imagine to be a particle, which is thrown against the gravity field. So this is the gravity field. Against the gravity field, you are throwing this ball with certain velocity, say u0, making certain angles, say theta naught, with the horizontal direction. And now you see that the motion, subsequent motion of this ball will be a parabola, that you know from your knowledge of physics. So in this case, therefore, the motion of this body, in order to study it, we not only require the, say for example, this direction, the horizontal direction. Let's say this horizontal direction, we call it as x-axis. We also require the vertical direction, that is termed as the y-axis. So in this case, we have the motion is taking place along two directions, and therefore this motion can be called as a two-dimensional motion. Obviously, 2D motion will be little bit complicated than the one-dimensional motion. One-dimensional motion is very simple. and just only, the motion is taking place along a straight line. So sometimes this motion we may call it as to be the rectilinear motion, because in case of rectilinear motion we just require only one axis to discuss this motion. And then obviously the third category will be the three-dimensional motion, or sometimes it is called the space dynamics. In general, the motion that we see in and around us is basically a three-dimensional motion. For example, the oblique motion of the cone that I was mentioning, this motion of this type of things fall under the category of three-dimensional motion or the space motion. So this is actually the real motion is taking place in 3D. So that's why it's termed as the space motion, and it is pretty clear that this is the most the complex type of motion that we need to consider. The little bit simplified is 2D and more simplified is 1D. So now I come to our scope of work. That means in this present class we need to study as usually both kinematics and kinetics. That's clear. Next, majority of our attention will be focused on to the particle, and then we'll have to discuss the rigid body motion also. Correct?
Yes, sir.
But in this classification, yes, in this classification, we need to discuss the one-dimensional motion. That will be obvious. We have to discuss the two-dimensional motion, and in this semester we do not have to discuss the 3D motion. So this will be covered in your next class. I mean to say in next year, when you will be studying the advanced dynamics. In that case, you see this 3D motion of the rigid body or the space motion of the rigid body will have to be covered. So therefore our present scope is particle and rigid body kinematics and kinetics, and we will be confining ourselves to the discussion of the one-dimensional and two-dimensional motion. So this is our scope of work. You understand? If
yes,
you
sir.
have any clarification, yes, any query, yes, please feel free to ask me. So at any point of time, you should unmute and ask me the question. So this will be there, yes. So this will be there for the hour time. That is the thing. Now let us discuss quickly what are the prerequisites. That means what you need to know, prerequisites for the class. That means if you want to study the dynamics, what are the essential subject knowledges that you must be having? Obviously, first you need to have the knowledge of mathematics. That's essential, and up to class 12, differentiation, integration, little bit of the vector algebra will be required here. So that's the first thing. Second thing that you require is, of course, the basic concepts in physics. Basic concepts in physics. So I hope you have both these two very strong with you. If you do not, right, if you are not very confident about your class 12 mathematics, what you have studied, then my advice will be to just have a quick refreshing look at this CBSE class 11-12 textbooks. CBSE 11 and 12 textbook. I assume that basic mathematics knowledge, geometry, etc., trigonometry, etc., are all known to you. You are master on that.
Has it.
Yes. And then if you want to have, it's very good, quick, the comprehension of this, you can have it from the book by Resnick and Halliday. So you can have the things from there. And of course, thirdly, we require the knowledge of engineering statics. because the basic concepts of mechanics are force equations, force equation, moment equation, all these things you will require, require the knowledge on this particular area. And for the time being, we do not require right now the knowledge of strength of materials, because here all our assumptions will be on rigid body. So having said these prerequisites, having said about regarding the books, already I have mentioned that textbook is Merriam and Craig, Merriam and Craig, and Craig, that will be our main textbook. You can have the 7th edition, it is freely available in the internet. Else, if you want to have a hard copy of the book, you can buy, this is the latest edition, 8th edition, Indian edition. So you can have this. The beauty of these two books is, these two editions is that all answers of the problems are available in the book. So that is the main textbook. Apart from that, you may look into Beer and Johnston. I hope you know the names of these two.
Yes, sir. Yes, sir.
Yes, sir. For me.
Beer and Johnston, not some. In strength of materials, you have, correct. Strength of materials also you have Beer and Johnston, but here I am talking about the engineering mechanics, not the strength of materials.
Yes, sir.
You have a combined book, you have a separate book, but nowadays the combined book is more popular. So this is a voluminous book, in fact, encompassing both statics and dynamics. So Beer and Johnston. Then you have the book by Timoshenko and Young, Engineering Mechanics, Timoshenko and Young. This is also a very good book, Timoshenko and Young. Then you may have the book by Hiblar. Here also separate books and combined books are available. This is a combined book. Timoshenko and Young is a combined book.
So R.C. Hiblar?
R.C. Hiblar, yes. And the 5th one, I put a line here because they are the stalwarts, and the 5th book are written by the authors who are not the stalwarts here, they are the particles. So they are by Nag and Chanda. This is a publication from Wiley. So this book also you can see. So these are your, the books mentioned here. So these are your first thing that I need to consider for you. Now this is the the introductory part. Now let's go on to our business. So let's start with the first chapter. The first chapter, without much delay, the thing we discuss with, first we will talk about the rectilinear motion. So we'll start with, of course, the kinematics. So rectilinear motion means we will be discussing rectilinear kinematics. So as you know, what is a rectilinear motion? So we will be talking about the particle. So whatever I will be talking here, all will refer to the particle only. And then after the entire discussion of particle, we will transfer ourselves to the discussion of rigid body dynamics. So in case of the particle rectilinear motion, essentially what you see, that we have a mass particle here, and the particle will essentially move along a straight line. Say this is the straight line along which the particle is moving. Now the motion of this particle can be, of course, recorded. It should be recorded. How when I say that the motion is taking place, it means what? That you have a parameter called time, and with respect to this parameter called time t, which was totally absent in your discussion of statics and in your discussion of strength of materials, but here in dynamics we will be having, this is the primary parameter. So with respect to this time, you see the position of this particle will change, correct? Now how the position of the particle is measured? For that, you need to take a reference point. This reference point, we call it as the point O. Let us suppose this is our reference point. And this reference point is basically, is the origin of, this we can say, is the origin of an inertial coordinate system, an inertial system. What is an inertial system? Now this is, I am talking about when I am saying that it is an inertial system. See, when I talk about the coordinate, I must say, give the descriptions in terms of the 3-dimension, because actually we are living in 3-dimensional space. So let me call it with respect to the 3-dimensional coordinate system. Let's say this is the x-axis, this is the y-axis, and this is the z-axis. They are taken according to the right-hand triad rule. That means they are not taken arbitrarily, they are taken in a specific direction, and every time it should satisfy the right hand rule. That means x cross y must be z, y cross z must be x, and z cross x must be equal to y. So this is what is called as the right hand triad. Now this coordinate system, we can call it to be a rigid body. That means reference frame itself can be considered as a rigid body. And this reference frame, this being my origin, is placed on a place such that this either is absolutely fixed, that is, either it is absolutely fixed, it is not having any motion whatsoever, absolutely fixed, or it can move with a uniform velocity. With a uniform velocity, I assume that you have the basic knowledges of what is called velocity. So that's why before discussing velocity, I introduced this term to you. Uniform velocity means that it is actually moving with velocity whose magnitude as well as its direction is not changing, it's constant. So it is moving with uniform velocity or moving with uniform speed along a straight line. And number 3, does not have any rotational motion, does not have any, this is and, does not have any rotational motion. So these are the criteria, and any reference frame which satisfies this criteria will be termed as an inertial system, because we are basically, what we are studying here is called Newtonian mechanics, and in case of Newtonian mechanics, the concept of inertial reference system is very, very important, because Newtonian mechanics actually deals with respect to inertial system, and the Einstein mechanics, or what is called the relativistic mechanics, it discusses, of course, with respect to the relative reference frame, which will not be our cup of tea in engineering mechanics portion. So ours is a Newtonian mechanics, which is pretty pretty much applicable to any sort of motion that normally takes place around us. So that is the thing, that for us the concept of inertial system is essential. So let us assume that, and again I am saying absolutely fixed, you can argue that in this whole universe, right, there is nothing called absolutely fixed. But again, we leave apart those the high-funded debates and discussions, and we confine, we are little people, small people, we confine ourselves to the right now to the ground or the earth, mother earth, and we assume that our mother earth is absolutely fixed. That means on the earth we take a reference point which is not moving. So in that way, if we try to discuss this, of course these exceptions do occur, and when exceptions will occur, we will mention. But unless otherwise mentioned, we will say that the reference point which is absolutely fixed here will be posted on the earth. So let us say that we are That means we are considering the earthly motion. That means motion which is taking place on the earth. Strictly speaking, they are not absolute motion. They are actually the relative motion, but for the time being, we neglect the motion of the reference frame itself. That means the motion of the earth, and for us it serves the purpose of the fixed reference frame. So the point O is fixed on the earth, and the position of the particle is measured with respect to point O. Suppose at time t equal to 0, let's say t equal to 0, this is called as the time initial. That means imagine that I have a stopwatch and I just press my stopwatch on from this time. So that time t equal to 0. So I forget whatever events that have taken place before this. So I just record the events beyond time t equal to 0. So time cannot be negative for us. So we see that I like to have the position of this particle with respect to point O, and let us suppose that this is our position vector. This is our position vector, which we call as to be our initial position vector. So let's say this is our initial position vector. Suppose I call this vector as xo. Here, this is the vector x bar o that represents the initial position vector. Correct? Now, at any point after this type stopwatch is made to be on, then let us consider an arbitrary point of time. Let's say t equal to t. T equal to t represents an arbitrary point of time. Now, if the position vector of this particle does not change as time changes from t equal to 0 to t equal to t, then obviously I say that there is no motion of the particle. Correct? So the particle stays at all points from t equal to 0 to t equal to t at this position. And if that happens, then it will fall under the category of statical situation. Of course, we are not considering statical situation because we are studying dynamics. So for us, it is imperative that between these two time zones, the position of the particle is definitely going to be changed. So if I assume that, suppose at an arbitrary point of time the particle is here, then what will be its position vector? So obviously the position vector will be measured from the origin, and this is going to be my position vector. Correct? So this position vector I call it as x bar, and I use this to describe that this is a function of time. Since it is a function of time, the situation becomes dynamic in nature. So I have this x bar t. Correct? So then I say what will be my displacement during this situation? Obviously, the displacement of this particle during this time zone is this much. How much? It is from here to here. So this is going to be my displacement, right? So yes, So I can say this displacement. I write it as delta x bar, and again this will be a function of time. So how much will be my delta x bar here? So I can say delta x bar of time, which is a function of time, is basically equal to x bar of t minus x bar 0, right? Or we can say it is x bar within bracket 0. So this will be called my displacement. So so if this is my displacement and I agree to see that this displacement is basically a function of time, then I define a concept which is termed as the velocity. And then I'm quickly going through it because all these things are essential for us, but I will not waste many time in discussing this. So I'll be just recapitulating all your old concepts. So in case of velocity, what we say, we first find out that okay, this is the displacement that the particle is suffering between the two times, say t equal to 0 to t equal to t. So I can therefore say that the average rate of change of this displacement, right, will be equal to how much? Now that we can say delta x bar t divided by delta t, and this we can write it to be as Mohammad Javed, why you are so late? In the next day, I will not allow the people to enter into the class after 5 minutes, okay, because it will disturb the proceedings. Vishal, you should give this to notification in your group.
Okay, sir, I will take care of that.
Yeah. So this will be, the rate of change of this displacement, and I call this as to be the average rate of change of displacement. This will be termed as the average rate of change of displacement, because we are taking the averaging process. So it means that it will be, say, x bar t minus x bar t equal to 0. So I put it like that, x bar is written in this format, divided by it is t minus 0. In fact, you can have any two times here. Say time t2, you can call this as time t2, this t you can call it as t2, you can call this is as t1, then it will be x bar t2 minus x bar t1 divided by t2 minus t1. So this is what is termed as the average rate of change of displacement. Now if I make in this process, if I make this thing, if I make this delta t time to be vanishingly small, that means if I make this this one, limit delta t tends to 0, I introduce this thing here. So it is limit delta t tends to 0. Then from your basic knowledge of calculus, you note that this is basically nothing but is your dx bar dt. So this we call as to be our velocity, which is a vector quantity, and I use this bar sign to indicate its sense. So it means that if we move to our initial description, if the particle moves in this way, that means if this is our particle, then the velocity vector, if the particle goes in this sense, the the sense of the velocity of this particle will be represented by this vector. This is the arrow will indicate its sense, and you see here that this will be positive if this is greater than 0. That means if your x bar t, it increases with time, correct? If it increases with time, or in other words, if x bar t is a monotonic increasing function in language of calculus, then we say that the particle is having a velocity which will be carrying it further away from the origin, because then only you see your x bar t will be an increasing function, monotonically increasing function with respect to time. Now what will happen if the velocity is in this direction? So in this case, obviously the x bar t, this vector, the magnitude of this vector, right, it's going to decrease with respect to time, because the particle will move towards the origin. And since you are measuring your position vector from the origin itself, so it means that the particle will be moving from a further position to a nearer position. So it means that essentially the gap between the two positions, I mean to say the particle and the reference point, is going to decrease, and in that case this vector, the differentiation will come out with a negative sign, which means that if your dx bar dt turns out to be positive, this will be your sense, that means v is greater than 0, and if the particle moves in this way, then v must be less than 0. So this is the interpretation. So it has therefore some association of sense, magnitude and direction. So the direction is of course the x-axis, the magnitude is the magnitude of the velocity, that means if I take the magnitude of this vector, then this will be equal to v. This is sometimes also known as the speed of the particle. So it is also known as the speed of the particle, correct? So this is your this thing, and we see the sense will be represented by this arrow. So we have, therefore, you know that we get this particular thing. So you have you know the situation that we will be getting is you know just a minute. So this is the thing that we will be having the magnitude and the sense and the direction. The direction will be, of course, the x-axis. Magnitude will be the magnitude of the vector, and sense will be carried by this arrow. That means whether it is in this sense or whether it is in this sense. So that is about your velocity. So you can assume, you can very easily see from here that this velocity is also, it may be also a function of time. There can be two cases. Case one is that this magnitude of this velocity is not changing with respect to time. So that means if you draw a graph with x-axis as the timeline and the y-axis as to be your velocity, and if this graph happens to look like this, it happens to look like this, it happens to look like this, say this one. You see here, with respect to time, the magnitude as well as sense of this is not changing. So it means, therefore, that if this happens this way, then we call this that the particle is moving with a uniform velocity. We say that the particle is moving with a uniform velocity. Otherwise, if the graph is something like this, say for example a graph something like this, an arbitrary thing, then we say that the particle is moving with a non-uniform velocity. So the particle is having a non-uniform velocity. And if the particle is having non-uniform velocity, so it means it becomes a function of time. So now it can change with respect to time. So like the way I have derived the concept from the displacement to the velocity, in the same way, if we just imagine in place of displacement into this equation, if we just imagine that we put the velocity, because if we assume that the particle is moving with a non-uniform velocity, it means that with respect to time the magnitude of the velocity of the particle is changing. So it means that its vector is a function of time. Now see the other person, Inayat Ali. So next time you will not be allowed to enter into the class. So we see from here that if it happens, you know, in this manner, that means if it changes with respect to time, and if I substitute in the mathematical expression in the above, in place of displacement, if I substitute the velocity term, then we will come across another term which will be termed as to be the acceleration. We term this as acceleration. Okay, and in that case we define the acceleration in this manner: limit delta t tends to 0, it will be.
Achha, sir. My question, sir, I'm asking that whether that uniform velocity and constant velocity are the same thing.
Yeah, they are same, exactly. They are same. So if we have, you know, for the non-uniform velocity, particularly this will be meaningful when it is non-uniform, because if the particle is moving with a uniform velocity or a constant velocity, as he was telling, you see this result will be a null vector. So I am not talking about something which is null. So therefore this acceleration concept is particularly important when our particle is moving with a non-uniform velocity. So in that case, we have this limit delta t tends to 0, delta v bar t divided by delta t, and we term this as our acceleration vector, and I call it as a bar, right? Now, just like the previous scenario, if it is found that with time the magnitude of the velocity is increasing, if it is found that with time the magnitude of velocity is increasing, for example the curve that I have shown here, you see very well from the graph that as time passes by the magnitude of the velocity is actually gradually increasing. So in that case we say that the particle is moving with accelerated motion. On the other hand, if it is found that with time and for accelerated motion, we say that this quantity is a positive quantity. And if it is found that if with respect to time, say some velocity is having a curve like this, so it means that with time the magnitude of the velocity is gradually coming down. So in that case we say that v bar t is a monotonically decreasing function, and since it is monotonically decreasing function, if you differentiate with respect to time, this will be less than 0. And in that case we say that acceleration is less than 0. So this we will term as, this scenario we will term as to be the retardation. This scenario we will call it to be retardation, or we call it as to be deceleration, right? So retardation or deceleration is nothing but negative acceleration. Now nowadays the books, they do not mention categorically that you are having this is retardation or you are having deceleration. They simply say that the particle is having an acceleration minus this quantity. You understand? They do not specifically say that it is retardation or it is what is called is a deceleration. But there are some books who actually coin these terms. So these are actually the old the terminologies, but we still use them. But you may not use them. So you may have just only one term reserved for you, and its magnitude will be plus. In that case, the graph will be something like this. And if its magnitude is minus, then obviously the graph will be something like this. So that's the only, the point of difference between the two. You understand what I'm saying? So now, again, just like the case of your velocity, it may be that the magnitude of the acceleration and its sense may not be changing with respect to time. That means parallel to this graph, you may have a graph like this. Parallel to this graph, you may have a graph like this, where along the, this is the time, and here we are plotting the acceleration, and we find that the graph of the acceleration is something like this, or it is something like this, right? So in that case, in either of these cases, I find that the acceleration is not changing, correct, with respect to time. So in this case, we say that the particle is moving with uniform acceleration. Otherwise, the particle will be said to move with a non-uniform acceleration. So therefore, if we see from here that the relevant equations from here are all differential equations. So relevant equations, we can say that now I am suppressing the arrow sign, because in case of the rectilinear motion, the arrow is not that important. So we can proceed with the scalar descriptions also. So we just bring down from our equations from our vector level to scalar level, and we say that v is basically equal to dx dt, and we just now derive the thing, we introduce the concept of acceleration, we say that it is dv dt. So these equations we have just now seen. Now you see from here the Newton, when he actually wrote the Principia of Mathematica, in which he laid the foundation stone of what is today we are talking in this class, that is engineering, I mean to say not engineering, Newtonian mechanics. So he used this symbol. This is x dot, right? And right, so it is v dot. So he used this dot sign. So dot sign essentially means, dot essentially means that it is being ddt, that means differentiation with respect to time. And he used the term called fluxion in place of velocity. So all these were, that time, those were the descriptions of made by Newton himself in his Principia. But nowadays we use all other mathematical symbols in calculus. So you have, this is A equal to dv dt. So if I continue in that, because you see that that v is nothing but dx dt, so we can continue in that and say that it is ddt of dx dt, which we can write as to be our successive differentiation, and apply the concept of successive differentiation, it will give us d2x dt2. That means if I would have used the vector sign, then this vector sign would have come like this, this vector sign would have come like this, and this vector sign would have gone like that, correct? But if we do not use the vector sign, just use the scalar symbol, then we can use the scalar symbol in that way. So this is d2x dt2, and sometimes this d2x dt2 is also represented by the two dots, so x double dot. So these are the two ways by which we can use this expression for your acceleration. Now we have a third alternative for it. What is the third alternative? Suppose if I look at the scalar description of acceleration, so it is a, and a becomes equal to what? You see that we have just now seen that a is equal to dv dt, correct? If we take into the scalar description, this will be dv dt, the definition of our acceleration. So I could have written this equation in this manner, that it could have been dv dx into, I could have written it as dx dt. So here what we have applied is known as the chain rule of differentiation. So that dx dt stands for velocity. So ultimately we see that it is written as v into dv dx. So this is the way I write the scalar equation for this acceleration, correct? So this is the way we have written, yeah, and its vectorial form should be equal to, it should be equal to v bar into, this will call it as dv bar dx. So this is the way we can write it, this thing. But that as I was mentioning, that the vector description is not very important in our what is called in our rectilinear motion study, where that the sense is very well defined. So you see, therefore, without much adding any complexity within our description, I can write these expressions like this. So summarizing, we can therefore say that our initial rectilinear motion equation toolbox is something like this, that we have described the velocity, we have described the displacement, then we have described the velocity, which is equal to dv dt, dx dt, sorry, so I write it like that. So this will be dx dt, this is our toolbox, and the magnitude of this is termed as the speed, I say, and then we have the acceleration, which I have written it as dv dt. Alternatively, it could have been written as d2x dt2, or alternatively I could have written it as v into dv dx. So this is the way I just write my toolbox here. So these are your equation toolbox. So far we have studied. What about their units? What about their units? So we will be basically using the SI unit. So this standard internationally will be our default unit here. So accordingly, the unit for the displacement will be either in millimeter or in meter. But actually, truly speaking, if it is SI, then you need to use meter. This is the preferential unit. But there are occasions where we can express it in millimeter form, or we can express it in even in the kilometer form. It depends. If the meter is too large a unit, then we reduce the unit to the millimeter form, or if the meter becomes very small unit, then we may go for the kilometer form. So that is the thing. And similarly here for the velocity, the preferential unit will be the unit will be millimeter per second, but the preferential unit will be meter per second. Meter per second will be the preferential unit. However, you can have the units like kilometer per hour. This also is used. And many times if you see the problems, you will find that in the description of the velocity, the unit that has been used in the kilometer per hour form. So in order to convert the kilometer per hour form to meter per second, what you need to do is you need to multiply it by 5 by 18, because kilometer means 1000 meter and hour means 3600 seconds. So basically, you know that this will be, these two will be getting cancelled, and if you divide it by 2, then the result becomes 5 by 18. So therefore, the factor will be multiplied by 5 by 18, and if it is in meter per second, you need to convert it in kilometer per hour form, then you need to multiply by 18 by 5. Quick conversion will be there. So that is about your unit in velocity. And what about the unit for acceleration? It is very well known that the acceptable unit for acceleration is meter per second square. However, there are occasions where you can have the unit like millimeter per second square, or you can have the unit like kilometer per hour square. Although this is a very rare unit, but there are instances where people can also go for this sort of, the unnatural, I should say unconventional unit. But again, the preferential unit, these are your preferential units where I am putting this arrow. These are your preferential units for the SI system. So whenever you need to report your answer must be accompanied by the proper unit, otherwise marks will be deducted, because every physical quantity needs some unit to be to have its specification. So therefore, you see, these are your basic equation toolbox that we say. So here our description is very simple. We can think in this algorithmic way. The flowchart can be like this, that you know the displacement of a particle, right? You need to find out the velocity. So this will be your flowchart, right? And then you need to find out your acceleration. So this is the way we normally move, and the process is very simple. That is, the differentiation will be the case. Now the question arises, what will happen if the reverse information are being given to us? That means in this flowchart, we started from displacement and ends up with acceleration. Now I just make it topple upside down. That means the thing is something like that. Your information level is acceleration. This quantity you know as a function of time. You are now required to find out what will be its velocity and what will be its displacement. Now in this case, we will be continuing using this equation, but in some other form. So let's look at how to find out all these things. Say we start with acceleration. Supposing that acceleration is known to us as a function of time. So since acceleration is known as a function of time, I write like this, it is dv dt. I continue to use the scalar description. So dv dt will be equal to a of t. Now what I do is I do the method of separation of variables, and I write this in this form. It is dv equal to a of t dt. So I use the concept of differential in calculus. I have this, and now I will be integrating it like this. So it will be integration dv, that will be equal to, it will be integration a of t dt, and then there will be some integration constant, that is c. So if I perform this integration, the result becomes equal to v equal to integration a of t dt, correct, plus the arbitrary constant of integration. Now how to find out this c? Now it is simple, that you need to know what is the initial velocity of the particle. This information you must be knowing, and this condition is termed as the initial value problem. So I must be having, suppose we know the initial velocity of the particle. That means suppose v0 is the velocity of the particle at time t equal to 0. So let us write it in this manner, that it is the velocity of the particle at time t equal to 0. So if this is known, right, so if I put t equal to 0 inside this expression, so from there I will be definitely getting the velocity, because it is containing all the time factors here. So you may have all these time factors here, and you can see from here that c must be equal to your v0, because if you put t equal to 0, this integration vanishes, correct? So
Yes.
we have therefore c equal to v0, and in that case we can write therefore say that v must be equal to, that this will be some v0 plus this function. So let us call that this function, let us say this function, we write it like this, say it is vt plus c, and assume that f of 0 is 0. So in that case, you see our equation becomes equal to v is equal to v0 plus this is, this becomes equal to f of t. So this is the expression that we are getting. So we integrate the acceleration equation with respect to time, and what we are landing in this level, that we know the velocity. But in landing from acceleration to velocity, one additional information must be known to us, and what is that? This v0. So this information must be known to me so as to get the expression for the velocity explicitly. You understand what I am saying? Now,
Yes, sir.
yes, very good. So now I can say that this v is basically nothing but this is dx dt. So again, if I continue changing my variable, separation of variable, I can therefore say that it will be v dt, that will be equal to v. I can write it this way. I can write it in this way. So I can say from here that this is dx dt. So I can say that v dt should be equal to our dx. So dx is equal to v dt. So we can write that this should be equal to v0 plus f of t whole into dt. That means I can write it as, say, distributing this dt, I can say this will be v0 dt plus f of t dt. So I write like this. Now if I integrate it again, okay, so then what we will be getting is integration dx, which will be essentially equal to x, that will be equal to integration v0 dt plus it is integration of f of t dt. So it is called successive integration dt. and plus we will be having some constant, let it be c prime. So it essentially means that I write from here that it essentially means that it is x equal to v0 t plus you have this double integration. It's not double integration, it is called successive integration, f of t dt and then dt, and then you must be knowing what will be the value of c prime. So in coming from this velocity to displacement, one more additional information should be known to you, and that is regarding the specification of the initial displacement of the particle. And quite often you see this c prime turns out to be as x0. So ultimately what you get is these two equations. So one is v equal to v0 plus f of t this way, this is one equation, and another equation is this. So you see from our foregoing discussion that if we reverse our initial information level from displacement to acceleration, that means just if we revert back, the process becomes just the process of integration. So you need to find out the integration, you need to carry out these integrations to find out your expressions. Now these are all starting with the assumption that we know acceleration as a function of time. For example, if we say in the above discussion, if we consider a special case, what is the special case that we are going to consider? That our a is equal to constant, correct? So if we assume this a to be equal to constant, then you can see we can come from here, since this is being constant, so I can start from this equation and can definitely say from here that v must be equal to v0 plus at. How it is coming? You just put in place of at, you just put a, and since it is constant, so a will be coming out of the integration, so it will be a into integration dt, and that is nothing but at, and therefore the initial velocity, if it is v0, then v becomes equal to v0 plus at. T plus half a t square, correct? So I think it's very simple to get these expressions.
Yes, sir.
So, yes. So these are very famous equations, because from your class 9, even nowadays in the schools, these equations are taught as below as in the class 9. They start from class 9 or maybe class 8. So you see, now there is one disadvantage. If you start so early with these equations, there is a disadvantage. What is that disadvantage? Because it is being seen, it's a long experience of checking the answer scripts for last 20 years, it has been noted that people often commit mistakes by writing these equations to the cases where acceleration is non-uniform. That means, suppose I am giving a specific example. Suppose in some problem it is mentioned that a is equal to 2t minus 3t cube meter per second square, and t is in seconds. This is the description. Now people ask you that if the particle starts initially from the condition of rest, right? Initially condition from rest, if the particle starts, what will be the velocity of the particle at the end of 3 seconds of its motion? Say if this is a problem being given to you. Now it has been noted that in such type of problems also people use these equations, which is absolutely wrong, because these equations are applicable only when your acceleration is a constant value. But here it is seen clearly from the description of the acceleration that acceleration is not going to be not going to be constant. So therefore, these equations are not at all applicable to this type of problems. So you should be very careful, not to commit this type of error. But I'm telling you that every year I find at least one answer script where this type of errors are being committed by the students. Sorry, it will be in meter per second square. That acceleration equation I wrote mistakenly. I wrote it meter per second square. Okay, then fine.
If there will be, I think, F will ATDT.
In this case,
Yes, sir.
oh, acha. Yes. Double integrate. It should be. Yes, it should be 80. Correct. Thank you. So I need to write here A. Correct. I need to write A. So I just put it as A here, A here. Now it's okay, nah? So, so this will be the situation for acceleration equal to constant. Now this is one type where acceleration is known as a function of time. Now it could be that acceleration may be known as a function of velocity. So that can be case 2. So that is case 1, and let us say this is case 2. So this is our case 2 and this is our case 1. Let's write it like that. So you see this is case 1. Case 1. Okay. This is case 1 and that one is case 2. So if the acceleration is known to be function of velocity, so it is being given A is equal to A of V. So in this case, we can find out the velocity. How? Very simple. Just like in place of acceleration, we write this so-called differential equation. So we say that A becomes now equal to V dV dx. So it is pretty simple from here that you separate your variables. So it is V dV is equal to A dx. Now you integrate it. Now you integrate it like this, and you have an integration this way. Now I use some alternative form of this. That means in doing this, you must be knowing the specification of velocity at some point of displacement. That means, say we given, so this we need to find with this additional information, because if this information is not being given, I cannot find out the expression explicitly. So it is being given that at x equal to x0, say v is equal to v0. Say it is being given. So in this case, I could have integrated this expression, and then I could have found the constant of integration by putting this. That is one step that I have described in my previous board work. But now I change my board work. I do not follow this method. What I do, instead of doing this in this way, I just apply the concept of definite integral like this. I integrate it between the limits from v0 to v, and this one from x0 to x. Now I assume that at x equal to x0, v equal to v0 is being given, and I assume that when x becomes equal to x, that means an arbitrary displacement, v becomes equal to v. Correct? So in this way, I can alternatively, I could have done this way, but alternatively in a short form, I could have written it in this way, and I ultimately, what I can see from here, I can see that it becomes v0 square minus v0 square becomes equal to 2 times integration from x0 to x a dx. a dx. So this is, you know, is sorry, here it is not function of velocity. I'm sorry. This one will be function of displacement. Sorry. So I have written it wrong. So it is AFX. Sorry, not function of velocity. It is written in this way. So you see, if you know the the acceleration, that means if you write it in this way, it becomes 2 integration x0 to x. It becomes a of x dx. So if you know explicitly the variation of acceleration with respect to x, you see, you can integrate it to write that. Now here again we have a special case. Special case is that if your a becomes constant. So special case is that, now I write it in black color, that if a becomes constant, if a is equal to constant, in that case we find that the expression for the velocity will be given by v square minus v0 square. That will be equal to how much? That will be equal to twice a into x minus x0. So this will be my expression for the velocity. So I can say the velocity at any point of time, at any level rather, can be given by this expression, that it is equal to square root of v0 square plus it is twice a into x minus x0. So this is the way I can find out if your acceleration becomes constant. So that is our case 2. That means when is your acceleration is known as a function of displacement. So this is very important. Acceleration, when it is known as a function of displacement, we can calculate the velocity in this manner. Now you can of course have the next level. That means if you know explicitly how your acceleration is varying with x, you can ultimately make that integration and express v as a function of x and use that that equation to find out your displacement by writing in place of v, just write dx dt. So if I write v in place of v, if I write dx dt, and if on knowing the explicit variation of acceleration as a function of x, I could make that integration possible for me, and ultimately I can express the velocity as a function of x and can carry out my process. So that can be one thing. Now, if this is being done in this manner, let us quickly go into the next type of variation, that is case 3, in which you see case 3 in which we have acceleration known as function of velocity, which I mistakenly earlier wrote. That acceleration is known as a function of velocity. So in this case, when acceleration is known as a function of velocity, we see from here we continue to use the equation dv dt, that's equal to a, and a is known as a function of velocity. So again we do the separation of variable and can write that dv divided by a of v, this time because this is known as a function of velocity. So you just write it this way. Again the information must be given that at t equal to t0, specification of velocity may be given to you. So in this case, if we integrate this equation, then what will happen? So it becomes therefore t minus t0. Now I am doing it in one shot. I hope that this will be pretty clear to you now after such a long discussion. So you see this will be integration from v0 to v. So it will be dv by a of v, correct? And this becomes t minus t0 is this. So ultimately t becomes equal to, t0 plus T0 plus this thing. So from here we can find out the expression for the velocity. So the result will be now, this result we can write that ultimately V can be expressed as function of time. Correct? Together with this knowledge. So ultimately, yes. So ultimately from this analysis we can find out the velocity as a function of time. We can use this expression. In order to find out the next level. That means I can from here I can now find x as function of time. Now, since I know that if v is known as a function of time, how to find x as function of time that is already being described? Easily can calculate the expression for this one. So that is number one. Number two is that I could have alternatively written this equation in this manner as well. So it is v dv dx that is to be known as a of v. Correct? I could have written it in this manner also. So the question is, when I will be going to use this equation and when I will be going to use this equation. That might be your question. Now the selection of whether you are going to write your acceleration in this manner or whether you are going to write your acceleration in this manner depends primarily on this level of information. See here, what was the information being given? It was the basic at time t equal to 0, it was prescribed, the specification of velocity has been prescribed. But in this case, obviously, velocity will be prescribed at the displacement level. That means at x equal to x0, v will be specified as say v0. So if this sort of specification is there instead of this specification, so then it will be prudent for us that we should use this the differential equation to start with. So if the mathematical process, it is simple to see that it will be x minus x0 will be integration from v0 to v, it will be v dv divided by a of v this way. Either, and also you can write this as half of integration from v0 to v, we can write this to be equal to d of v square divided by a of v. If you write in this way, then your limit should be changed from, because your fundamental variable has been changed from velocity to v square. So you can write like that. Of course, this description will be helpful if acceleration is actually expressible as a function of square of the velocity. That means instead of, actually a is a function of velocity, no doubt about it. Say, for example, this a is being given as v to the power 4 minus, it is something like that. I can, of course, describe it to be function of velocity. Also, I can describe it to be the function of the square of the velocity. So this particular, the selection would be helpful for us if this expression for acceleration contains the even integral powers of velocity. So you can write it something in this way. So then this will be helpful, or otherwise, of course, you could have used this equation here as well. But this way, if you do this, then your integration will be shortened. Correct? So that is the thing. So you see, this is the the description for case 3. And once again, I repeat the thing, since ultimately v is known as a function of x. So your specification becomes totally complete. So therefore, you see, when a is a function of velocity, you have two alternatives with you. Of course, which alternative you will be going to use, of course, depends upon the entry level specification, what is being given, and in terms of initial situation. That becomes our case 3. And finally, when we have case 4, now in case 4, we will be having, say, acceleration as it will be a combined function, right? It will be a combined specification, so to say. What will be the combined specification? It could be the combined specification of velocity and time. So it can be a combined specification of velocity and time. So you see your equation then becomes, something like this, that A becomes equal to, this dV/dt. I can use this equation dV/dt. And since this A is known as a function of velocity and time, for example, just for example, let us consider that acceleration is, say, known as to be 3v square plus 40, and just a kind of arbitrary thing I am talking about. Actually, this type of problems are there in the book. You may come and solve it there. So you see your expression then becomes equal to how much? So your expression then becomes equal to, this becomes equal to p square plus 40. So ultimately, you see that your expression, not say 3v square, let me say it is 3v plus 40. Let us say it like that, 3v plus 40. So in this case, in this example, this is an arbitrary example I am talking about. So in this case, you can, of course, write differential equation as dV/dt plus minus 3 into v equals 40. So you see, if you compare this differential equation, actually it comes to the Leibniz linear differential equation. So it is dy dx plus p of x into y is equal to q of x. So this is of this form, right? If you compare it,
yes sir, yes.
Right. So it is actually being written. It is actually being written. I think I have written it in a wrong manner, na?
Yx y
dy dx. Once again, it will be v dV/dt. X again. dV/dt. Then it should be time. So here it will be a time factor. So it will be a time factor. It will be x y q of x.
p y of x. P y of
No. Okay. It's all right. Because if you see y in place of v, you just take this y. So this y, and here this v is there. So p of x, right? This is constant here. This is minus 3. P of x is this, and this is your time. So this is there. Correct? So it is there like that. In order to integrate this, you require that integrating factor, from your knowledge of mathematics. You know better than me that it will be e to the power integration px dx. So multiply this by this integrating factor into both sides of this equation, and you will be able to solve this. Correct?
Yes.
Is it okay?
Yes sir.
Is it okay?
Yes, sir.
You understand how that is done? So you see the provisions of Leibniz linear. So this is called Leibniz linear differential equation. So it may be there when there is a kind of mixed mode of description, specification of acceleration being given to you. This one is little bit of awkward type of description. Now you can have a power here also, because if you have power, then actually your equation becomes dy dx plus px y to the power n is equal to q of x. So this type of differential equation is known as Bernoulli differential equation, and this type of specification, that means I initially started with v square, writing it v square. So that v square term can also be there. So a equal to 3v square plus 40. So there can be this power of velocity term can also be there in your description, and accordingly you need to apply the Bernoulli equation. This equation is known as Bernoulli differential equation. First you need to divide all through by y to the power n. That means it should be y to the power minus n dy dx plus p of x is equal to q of x, something like that. and then you need to substitute the variable. So just open your differential equation book by the calculus book. Yes.
Y dash px into y is equal to qx y to the power n. ওটা y to the power n টা qx এর সাথে আছে তো এই বার্নৌলি যে ডিফারেনশিয়াল ইকুয়েশনটা
px y আচ্ছা এটা qx y to the power n টা এখানে আছে
হ্যাঁ এটা y to the power n টা এদিকে আছে
yes y to the power n টা এখানে থাকবে নাকি এখানে
qx এর সাথে থাকবে
এই okay. So you may have, the occasions where you can be using this, using this Bernoulli equation as well in order to solve this. So you see, all sorts of mathematical descriptions can be there, and particularly this type of problem is there in the book of Merriam and Craig. And after this today's discussion, I think you should be applying this equation to discuss this thing. Now, to wind up the first chapter, let me here just mention another special case, and that special case is known as, this special case is known as the motion under gravity, special case. So, motion under gravity, this situation, motion under gravity, this situation falls under the rectilinear motion if we neglect any air resistance, correct? That means what I mean to say is that when you are in the gravitational field, how you understand the gravitational field is there? Say this is your g. It means your acceleration due to gravity, it's acting downward. Let's say this is a reference ground. This is a reference ground. And you have a ball here, right? And you are throwing this ball up with certain velocity, say vg. So the ball moves up, attains certain height, and then it again falls down. So this type of motion is known as motion under gravity. And in this case, you see that this comes under the description of the rectilinear motion with uniform acceleration. Correct? That means when you are basically ascending, your description is what? Your description A is equal to minus G. Why it is so? Why it is so? Because when you are ascending, you see your particle, you can consider that this is your particle, right? So you are moving with your, so this will be, I mean to say, this will be your, suppose if I consider this is my reference frame, this is my reference point, so this is my reference point O, and from here I am talking about the initial position of this particle, not initial, sorry, the arbitrary position of the particle. Let's say this distance I call as the y-axis, so I call this as y. So when I say that this is my displacement, it will be obvious that I am talking about the velocity in this description, in this direction, and I am talking about acceleration in this direction. In reality, it may not be. Correct? It may be that your V is acting downward, it may be that your A is acting downward. Only thing, then you need to put a minus sign because you are specifying your sense of displacement in the upward direction. So anything up is considered to be plus. Anything down is considered to be minus when you are specifying your position like this. So this is very important, correct? So it means that suppose if you are throwing this ball from an elevated location, say this is a table, correct? This is a table, and from this table, basically you are throwing up this ball with certain velocity. So what will happen? After some time, it goes up and say it will fall down like this. Let us assume that it penetrates. So it falls down like this. So at any point of time, if the ball position is here, and if you are continuing your measurement of displacement in this direction, then obviously the position of this ball here after certain time will be considered with a negative answer, right? So if the ball is here, then the position of this ball will be, considered as plus. But when the ball goes down from your reference point, you see the position of the ball will be minus. So in our previous description, we find therefore that in this case my acceleration is having a minus sign, because actually my acceleration is acting in the downward direction. So you can use this minus sign. With this minus sign, you can go enter into your description and should write your equation that V should be equal to V0 minus GT. Then your V square is equal to V0 square minus 2GY, and then Y is equal to V0T minus half GT square. So all these equations you can use because you are able to apply your acceleration is equal, A is equal to minus G. So, and if it falls down, then of course you can consider that to be as plus and consider your scenario in that way, right? So this will be therefore comes under the descriptions of motion under gravity, which can be considered of course as the one of the the subsets of the rectilinear motion. So today, up to this point of time, we we just finish our recording at this point of time, and in our next class, when we will be